We are on our second day of section 1-2, and yesterday's notes were long and had a lot to do with talking about the domain pieces. So we're down to about there in our list of objectives. You know, we represent functions numerically, graphically, and algebraically all the time. And we determine the domain, implied and relevant, and the range of a function. Well, we're not done with range yet. We've talked a lot about the implied domain being just the math without any knowledge of where the formula came from. And then the relevant domain is, hey, this is a word problem, so I actually have to think about what x values would go into this. So what we did was we went through many 2 pages of examples that had to do with domain. Because of the two, domain and range, really domain is the one that takes the most time and the most effort. If all else fails with range, you can always graph it and then determine what your y values were, your dependent variable, and your range. So to find the range of the function, look for all y coordinates that correspond to points on the graph. A good approach is to use graphical and algebraic approaches simultaneously. Absolutely. So here in a little bit smaller print, you see, keep in mind that in calculus, you're often not allowed to use that calculator to do that visualization. So you have to know what the function looks like in your head. So throughout the year, you should be trying to get an idea of the shape of the graph before you grab your calculator. And yeah, we do that quite a bit in this first chapter. Example 4 says, finding the range of a function. So, I'm supposed to figure out what the range is of this, and I see that it has division. And any time that we have a polynomial divided by a polynomial, that's going to be a hyperbola. So we're going to see a hyperbola here. And then I started thinking about that 2. And when the number is a 1, up on the top we get our parent function, 1 over x. As those numbers increase, they pull away from the origin a little bit more. And one thing I notice about the domain right away, domain of f, is going to be that we can't use 0. Because we can't divide by 0. So I would just make a table to remind myself of hyperbolas and how they work, do a few of the negative values. Not going to put 0 in my table. I just got done saying that is a restriction on the domain. And then see what happens. So if we put a negative 3 down there, we'll have a negative 2/3. If we put a negative 2 in there, we get negative 1. And if we put negative 1 in there, we get negative 2. So that's going to give us one branch of our graph. And then if we put a 1 in, we get 2. Put a 2 in, and we get 1. And put a 3 in, and we get the 2/3. And we start to see the symmetry that happens with hyperbolas. So negative 3 and negative 2/3. Negative 2 and negative 1, negative 1 and negative 2, and there's my first branch, like so. I want to make it appear that it approaches the asymptotes, but never actually crosses them. You have to be really careful with that. If you cross an asymptote, points are lost. That's how it goes. I spent a lot of time in college studying hyperbolic functions, and hyperbolic functions are fantastic. I mean, there are so many unique shapes that can come out of hyperbolic functions that can help you do things like animation. So hyperbolic functions, very cool stuff. So this is what I have so far. I've got my 2 little branches there. And I start thinking about the fact that x couldn't be 0. And I see that, you know, in my asymptotes, I see that piece. You can't have 0 something. It won't make it there. But then I notice when I start thinking about what y values I can't have, we're never going to quite get there. And that's a y value of 0. So if I'm going to talk about the domain, I better finish it up and also talk about the range. My domain was that my x can't be 0. Now, my range is that my y can't be 0. Capital R for range of f. And we want to turn this one into interval notation. So we'll go from negative infinity up to 0, jump over 0, and get back on the number line and go to infinity. Now what we want to do is confirm this algebraically. So we want to figure out, when will 2 over x equal 0? Well, that's really close to a proportion. Let's put a 1 under there and let's cross multiply. 0 times x is 0. 0 does not equal 2. Yeah, it can't happen. This has no solutions. So we're verifying, basically confirming algebraically what we see there. So remember that hyperbolic functions show up from division. And if you have a positive a value, which would be the value on top, I hope you remember, it's been a long time since you saw that very basic model of a hyperbola. It's just in one section in Algebra 2. But a over the quantity x minus h plus k. And that a value, if it's positive, tells you first and third quadrant. And if it's negative, it tells you second and fourth quadrant. And again, the higher that the a value is, the more it pulls away from the origin. If it's a fraction, then it's going to get closer in to the origin. So again, things we want to visualize in our head so that later on we'll think, okay, this is what this should look like. Now, day 2, because we just got done talking a little bit about range, but we're going to continue talking about that. We're also going to discuss continuity as one of our objectives. And it says one of the most important properties of most functions that model real-world behavior is that they are continuous. In order to perform certain calculus functions, certain calculus operations, we have to have a continuous function. So we want to work with those, and if they're not continuous, we sometimes work really hard to figure out how we could explain it as a continuous function so that we can do the math. This means that a function is continuous at a point if the graph does not come apart at that point. So if you want to know if a function is continuous, an easiest way to think about how continuity works is, if you can start drawing the function and you never have to lift up your pencil and move it anywhere, well then it's continuous. If you have to stop because your function has a break, a jump, something along those lines, this is not continuous. So if you can put your pencil down, keep drawing the whole function, then you're okay. So like this says, let's look at a few examples. And again, there's your book, not putting arrows on there. We definitely need those arrows. This graph is continuous everywhere. Well, let's check that out. I'm going to put my marker on here and I'm going to draw it from arrow to arrow, and sure enough, I did not ever have to lift up my marker. Notice that the graph has no breaks in it. This means that if we're studying the behavior of the function f for x values close to any particular real number a, we can be assured that the f of x values will be close to f of a. So what that's saying is, at no point did the graph suddenly jump up in the air or jump down and gave us the feeling that, wow, that really doesn't look like it belongs, because that's what discontinuous functions do. This one, straight across, continuous. Continuous at all x. There is no x value that has a hole in it. There's no x value that has an asymptote, any kind of break whatsoever. This is continuous at all x. And I'm going to go ahead and put the arrows on here because that'll drive me bonkers. And it's one of the things this book does, because all the images of their graphing, they do with what they call a grapher, which would be software. And just like we don't see arrows on our graphing calculator, you're not going to see arrows on that software. So this one says compare the next two. And I see a problem. Look at this little f of a way up here. That's not good. We would have expected it to fill in that little dot right there. but it doesn't. This graph is continuous everywhere except for the hole at x equals a. If we're studying the behavior of this function f for x values close to a, we cannot be assured that it's going to fit right in line with what's going on with the graph's y values. And that's what they mean when they say that the f of x values will be close to f of a. In this case, we've got this big jump. So in this case, f of x is smaller than f of a for x near a. Now, that's because we see up here is apparently where this graph goes. And we expected it down here, where it would have been smaller. This is called a removable discontinuity. How is it removable? Well, if we just fill in the hole, we tell people, hey, you know what? At A, make it this. And we can plug that hole up. So if we have a hole that we can just say, define a domain for, then we can go ahead and say it has a removable discontinuity. And that's what's going on here. So this one is removable because it's a hole. All we're going to do is fill that little hole, and we could get rid of that discontinuity. The next one, look at that. It has a hole, and I don't see f of a anywhere. It's like it disappeared. Uh-oh. This graph still has a removable discontinuity at x equals a, because we could define this. We could tell people at f of a, let it equal whatever y value we have right there. We could do that, and then it would be filled. So this is also a removable discontinuity at x equals a. If we're studying the behavior of this function f for x values close to a, we are still not assured that the f of x values will be close to f of a. No, we don't even know where it went. There wasn't anything there for us. It's just a hole. And when you graph these, whether it's on homework or a test, you need to exaggerate that donut hole so that I can see that, yes, you knew that that point was not included on this graph. So in this case, f of a doesn't even exist. It's not there. It is removable because we could redefine it, like I did right up there, to plug the hole and make it continuous. So this one is also a removable discontinuity. And at this point, you'd be thinking, oh, well, both of those had holes. Holes are fillable, so they are both removable discontinuities. Yes, exactly. Oh, your thinking is so right. Good for you. This one. Uh-oh. That is not just a hole. That is a break in the graph at x equals a. That is trouble. That's called a jump discontinuity. So here is a discontinuity that is not removable. It is a jump discontinuity for obvious reasons. You know, we think logically in math. When you get to a, it just takes a jump. For some reason, as you're reading this graph from left to right, it jumps up. That's just what happens. So there's a jump in the function values that makes the gap impossible to plug with just a single point. There isn't just a hole that we could fill in. So this is a non-removable discontinuity. We do not have a way to define it at one point and fill that hole. Now look at the next one. And I hope you're thinking what I'm thinking is, oh, that's a hyperbola. That has two branches staring at me right there. That's a hyperbola. So this one has what's called an infinite discontinuity. And that's because it has asymptotes. Asymptotes are not removable, and they never stop. So they are infinite discontinuities. This is a function with an infinite discontinuity at x equals a. It is definitely not removable. You cannot fill in a hole and everything will be all right here. It isn't going to work. When the first graphing calculators came out, graphing calculators were made to try to fill in the gaps with the best information possible. And so we would see silly things like this out of the graphing calculator because it would try to connect those two pieces of the graph together. But we know mathematically, yeah, not going to happen. No way to fill in a hole and make that a removable discontinuity. So we have different vocabulary that we've talked through here about continuity. And like it says, the key concept from all of these pictures is that we want the point x, f of x, so xy, remember f of x is just fancy notation for functions, to slide smoothly onto the point a, f of a, without missing it from either direction, without lifting the pencil. Then it's going to be continuous. So this can be written using limit notation, which we're going to have to start to get used to because we're going to be using this. And our limit notation is actually a little bit of calculus here. So it says a function f is continuous at x equals a if, and we write it like this, the limit of f of x as x approaches a equals, so we think, all right, this means as I approach a, I want it to just go where it's supposed to go, which would be f of a. You put the a in, you get what's expected, then that's what should be happening. Otherwise, it is discontinuous at x equals a. If it's a whole, it's removable. If it is going to be one of our asymptotes, or it's going to be a jump discontinuity, we can't do anything about that. So those are non-removable. So some of the homework today is just going to be about the names, the vocab. Can you recognize what type of discontinuity something has, or is it continuous? Example 5. We're going to identify points of discontinuity. And it says, judging from the graphs, which of the following figures shows functions that are discontinuous at x equals 2? Are any of the discontinuities removable? Well, first, let's check out x equals 2. Let's see what's going on. X equals 2 is right here. Oh, yep, So, which are discontinuous? Well, this is one of them. So this is a discontinuous. All right, let's see if there's any others. I go to the middle one. No, that graph is totally continuous. That's fine. Yeah, there's nothing weird going on there. Now look below them, and we can see why. Look at that. Of course, you can't divide by 0. There's going to be a problem with the domain if you try to use 2. But here, there's no division. Yeah, that's just be a nice parabola, and that's what it is. Now I get to the last figure, and I see, uh-oh, there's a hole right there. So this is discontinuous. However, a hole we can fill in. So it says, are any of the discontinuities removable? Not this one. This is a vertical asymptote. We're not going to get rid of that one. But this one is a hole, so this is removable. It is something that we could fill, which would be great, especially if we want to work some calculus on it. Now, I look at all 3 of those equations, and I realize when I'm looking at this first graph that my domain, I'd have to say x can't be 2. So it looks like when we have a 0 in the denominator, that's where we're going to have an asymptote. And that's exactly what you learn in Algebra 2. We go to the middle figure. Like I said, there's no division here. There's no even roots. There is nothing that should affect the domain. It should be all real numbers, and that's what we see. But this last one, h of x, I notice that the numerator is factorable. That's a difference of 2 squares. That's x plus 2 and x minus 2. And then I have an x minus 2 on the bottom. By golly, those x minus 2's would cancel out. That's how a hole is created. So this one would have a hole at x equals 2. And then to figure out what the y value would be for that hole, we would take a 2 and we would put it back into the simplified function. Well, this was the simplified function right here when I canceled out those x minus 2's. So now it's h of x equals x plus 2. I put a 2 in here. 2 plus 2 is 4. It will have a hole at the ordered pair 2, 4. And that's another thing we have to be able to do. So if we can cancel numerator and denominator, those zeros cancel out, then we have ourselves a whole. So, algebraically, discontinuities come from x values that result in division by 0, the things that make the denominator equal to 0. If it is removable, it shows up as a hole in the graph. If it's non-removable, it shows up as a vertical asymptote or a jump. Most of the ones we work with will have vertical asymptotes, but if it's non-removable, it shows up as a vertical asymptote. Use the equation to find the x values that make the denominator equal to 0. Then analyze what the same values do for the numerator. So here's what they're saying. You're going to find a 0 in the denominator. If that same 0 shows up in the numerator, you got yourself a whole. If you find a 0 in the denominator, but it doesn't have the exact same 0 in the numerator, then you have vertical asymptote. So wholes only happen when we could cancel them out. That's when it happens. So that rule absolutely fits with what we found in example 5. For h of x, we can factor, and we can cancel. So this one had a hole. But f of x, I should use a different color here. No canceling. Occasionally, somebody tries to tell me that the x's can cancel. No, they can't. That's silly. Of course they can't. Canceling is a form of division. In order to be able to cancel, you have to see pure multiplication. That's not multiplication. My numerator has addition. My denominator has subtraction. That's not pure multiplication. We can't cancel anything out. So this one has a vertical asymptote at x equals 2. Extra example 5. Find the domain of each of the following, then find the discontinuities of each of the following functions. Classify each as a whole or a vertical asymptote. So now we're starting to see division, which reminds us, oh yeah, that's hyperbolas. So let me see what we can do here. So for A, I want to find the domain. Well, we can't use a 2 down there. I mean, that's going to be a problem. So the domain of f in set builder notation would be x, such that x can't be 2. So there's our start, just thinking about domain like we have been. And then I would want to try and factor and see whether or not the x minus 2's are going to cancel out. So let's see. 2x times x will give us 2x squared. I don't have a lot of choices in the back. It's either negative 1 and 2 or negative 2 and negative 1. And I realize if I put negative 2 out here, outside times outside will be negative 4. And negative 1 in here would give me one more negative x for a grand total of negative 5. And that gets me my middle term right there. And look at that. X minus 2's would cancel. That means this is a whole. And then we want to figure out, where is that whole? So if we want the whole, we have to go ahead and put in that 2 that we found earlier, and that again was the 0 of the denominator and of one of our factors up there in the numerator. And then we have to put that into our simplified version of f of x. And our simplified version of f of x is now just 2x minus 1. So you'd put a 2 in there, and 2 times 2 is 4, and 4 minus 1 is 3. So we would need a big old hole on our graph at the ordered pair 2, 3. Now, we found the domain. Find the discontinuities. So the discontinuity is at x equals 2. And then, I scrolled up too far here, classify each as a whole or a vertical asymptote. We already did that. It's a whole at 2, 3. So now we've covered everything. We have the domain, we have discontinuity, and we already declared that it will be a whole because we could cancel it out of the numerator and the denominator. B. Hey, look at that. Denominator's the same. Cool beans. That's going to give me my domain. Again, we'll do this in Set Builder. Set of all x such that x is not 2. So we can stop right now. This time let's put discontinuity at x equals 2. The question is whether or not it will cancel out. If it'll cancel, then it's going to be our whole again. So let's try it. All right, 2x squared. We can't factor out a greatest common monomial factor, so 2x and x is it. And then in the back, I need two numbers that multiply to -2, but somehow are going to get me a +3 in the middle. So it's either -1 and 2 or -2 and 1. So let's see, we need a +3x. If we go with 2, outside times outside would be 4x. And a -1, x for inside times inside, total of 3x. Well, it's not going to cancel. That's okay. It's just going to be a vertical asymptote. So vertical asymptote at x equals 2. So we have the domain, we have the discontinuity, and we have classified it as a vertical asymptote. Now, the last one here, this one's a little more work. More going on. So t of x, let's go ahead and factor the denominator first. That's a difference of 2 squares, so x minus 2 times the quantity x plus 2. And then on the top, there's no greatest common monomial factor. It's not a perfect square, anything. We just need two numbers that multiply to -12 and add to -4. So think about what those numbers would be. We've got x minus 6 and x plus 2. Okay, so thinking about my domain for t, and I really wish they hadn't made that a capital T. That's, kind of a big no-no. It means that there were more steps involved in getting this formula than we are able to see, but we'll go with it. That's what they named it. We'll stick with it. So the domain, set of all x, such that, now there are two problem numbers, positive and -2. So x can't be positive and -2. And then we have to go ahead and say it is discontinuous, or there's a discontinuity at x equals plus or minus 2. And then we'll classify it. And this one actually has one of each. So the x plus 2's would cancel out. That means we have a whole at the 0 of that, which would be -2 something. Well, remember how we find the something is we go back up and say, well, what if we did cancel it? So what if these were gone? So put your -2 in. We're going to have a -8 on the top and a -4 on the bottom. -2 will be where our whole is at. And then the vertical asymptote is the other 0 that's not going anywhere. Our vertical asymptote would be x equals 2. And that's because our factor of x minus 2 is not going to cancel out. So if it cancels, we have ourselves a whole. If it doesn't, we have ourselves a vertical asymptote. And that's all determined by the fact that we cannot divide by 0. So the denominators of these, they give us some really big hints as to what we need to do. Now, we've got some extra examples here, and these are piecewise functions. Piecewise functions are something that usually we try to have the Algebra 2 teachers fit in the spring, and I totally understand that that did not happen. So I'm going to go a little bit slower with this than I normally would to get everybody to see what's happening here. Graph the following piecewise functions. State the domain, classify any discontinuities, and we're not going to graph them on the graphing calculator. This will all be done by hand, and you'll find out it is not the hardest thing that you've ever done in your life. So what we have to look at is it's a statement like you had back in geometry, an if-then, you know. You've got a hypothesis and a conclusion. Well, the if part is right here. This is telling us that there are two pieces to this function. One piece is going to work if x is less than or equal to 0. The other piece is going to work if x is greater than 0. So one of the easiest things to do is to put them where they should go. So when I see x is supposed to be less than or equal to 0, I think, well, that's over here on the left of the y-axis. I have to graph x minus 1 over here. And then on the right-hand side, that's where I'm going to have my x squared, because that's where x is going to be greater than 0. Now, totally up to you which way you do this. A lot of people, when they first have an experience with piecewise functions, the first time they've seen it, really like just making tables. And when you make the table, you put appropriate numbers in there. Here, for instance, this says x has to be less than or equal to 0. So it could be 0, but I'm not going to put down 1, and I'm not going to put down 2, because it has to be numbers that are less than 0. And then I'll put them through the equation x minus 1. So 0 minus 1 is negative 1. Negative 1 minus 1 is negative 2. Negative 2 minus 1 is negative 3. So when I graph that portion, that piece, this is why they're called piecewise graphs, I start at 0, negative 1, go to 1, negative 2, and negative 2, negative 3. And then I think, hey, if I had just used the slope backwards, I could have done this as y equals mx plus b. So I start at negative 1, but instead of going up 1 and over 1 for the slope, if I went left 1 and down 1 and kept doing that, that would give me the graph as well. So we have a line over there, and yeah, my little blue spots are not exactly easy to see today. So what I know is that from 0 on to the left forever, it should do that. Now the question is, do I want to include that point at 0, negative 1? And the answer is absolutely, because this side had the equals bar. So making that a little bit bigger and filling it in shows, yep, that's what I needed to do. Now on the other side, we have a different piece. And again, like I said, a lot of people like to start off with tables when they first experience these. So we can't put a 0 into this. The numbers have to be bigger than 0. And then we have to square them. And we know this is going to be a parabola. So we have our 1, 1, and then we have 2, 4, and 3, 9. And the question is, well, where does this whole thing start? Well, if we could include 0, it would have started at 0, 0. So it would have gone like that. But we can't include it, and that's because this did not have an equals bar. So we're going to make a big donut hole right there to show that we understand that we know that there's space. There's space there. That is not going to be included because it didn't have an equals bar. State the domain. Okay? Domain of f. Well, it's going left forever. We can put 0 into it because that's going to give us negative 1. We already did that. And then everything to the right is included on the graph. Oh, by golly, it's all real numbers. So I'm going to do this one with interval notation this time. Domain of f, negative infinity to infinity. Now, classify any discontinuities. Yeah, something at x equals 0 is going on there. Oh, that's a jump discontinuity. So discontinuity at x equals 0, and it is a jump discontinuity. Jump discontinuity. I'm not real good at writing below myself, am I? All right, now, I also want to find the range with you. I know it doesn't say that, but we're going to state the domain, classify any discontinuities, and at least with a couple of these, I might do it for all of them, we're also going to give the range. So the range. if I can fit it. I write way too big. So for the range, I see this is going to go down forever, but here where y is -1, there's a jump. So it's going to go from -infinity to -1. We can include -1. That 0, -1 was a part of our graph. But then it jumps up here to 0. And we can't include 0. And then it keeps going up forever. So -infinity to -1, where -1 is included. And then we have to jump up to 0 and go to infinity. So non-removable discontinuity, or a jump discontinuity at x equals 0. All right, let's try this one. Ooh, this is a 3-piecer. Ooh, good looking stuff here. Okay, so let's see. If x is less than 0, that's over here, then it's x minus 1. If x is 0, we graph 1. Oh, I'll put that one on there right away. That's this one. All right. Then, if x is greater than 0, we have to graph x squared. Oh, well, we just did that in the last one. Okay, so, again, you could either go ahead and use slope-intercept form. As you notice, this is a repeat of what we did at f of x here. Or you could say, I'm just going to use the slope backwards. Whatever you want to do, as long as you do it effectively, that's what I care about. So 0, -1, -1, -2, -2, -3. And then I realize, okay, it's going to go to the left forever because it said x is less than 0, but I can't include that right there. That's 0, -1. It didn't have an equals bar, so I can't do that. All right. Well, that's okay anyway, because x equals 0 is graphed at 1. You know, the hole is kind of filled in domain-wise. And then we go over to our x squared. And again, you probably already know the numbers that you need here, you know. So 1, 1, 2, 4, 3, 9 from the last one that we just did. And again, the realization is this does not have an equals bar. Normally it would go down here to 0, 0, but it doesn't have an equals bar. So this is really goofy. Look at what's going on there. But we have our 3 pieces, and we have them all graphed right. So let's think about domain. And this is f again. Well, we're using all the x's. The blue one is using everything less than 0. I've got a green dot up there at x equals 0, we get 1, and then I have more green going forever to the right. So -infinity to infinity in our interval notation. But there is a discontinuity. And it is at x equals 0. And it actually jumps twice. So this is a jump discontinuity at the x equals 0. It could also be argued that this is a non-removable hole. Even if we put points into our little donut holes, this would still have those discontinuities because it's not just one hole. It's a non-removable hole that we have there. Now the range of this one, let's take a peek. So the blue arrow says -infinity forever. Well, then we get to 0. Let's see. At 0, x equals 0, there is a point there. It's up there at 1. So that's included. And then we go to the positive infinity forever, but gosh, this was down here at 0, -1. And this is up here at 0, 0. And then we have this 0, 1 piece up here, up at the top. So there is a break between our -1 value, which is not included, and 0. For the y's, remember, is what we're talking about. But then it goes up forever. And basically when I'm talking about the range, I can just forget about this goofy little point here at 0, 1 because the graph already exists forever. So my range is going to be from -infinity to -1, union 0 to infinity. Because for range, we have to think about the graph this way. What's happening? Well, we're going down forever, but we do have a break in that graph, a jump discontinuity from -1 to 0. But then it's going to go forever and use all the other y's. So it's a different thinking than our domain piece is. All right, C. C changes it up a little bit, which is good. Probably getting sick of those same pieces that we saw every time there. So for x is less than or equal to 0, I'm placing it over here, and that's going to be my x minus 1 again. And they did change the right-hand side. X is greater than 0 is now x squared minus 1. Not a big change, but they changed it, so that's helpful. All right, so we had our x minus 1, and again, either make the tables. This time you can use 0, -1, -2, totally fine. And get those numbers again. And if you're wondering why we did this repeat business, because this is the first time that you've seen piecewise functions. So we want you to be able to use that thinking again and again. Again, at this point, if you're saying to yourself, you know what, I'd use y equals mx plus b. I'd start here at -1, and I would go left 1 and down 1. Yeah, whatever you want to do, as long as you can get that graphed. But it's one piece at a time. You have to look at the x is less than or equal to 0 and the x is greater than 0 as the place where it stops doing one thing and starts doing another. Now, I do need a dot here because that one had an equals bar. And yes, we could make a table again for this one. It will be slightly different this time because we have to square it and then we have to subtract 1. So we could certainly do that. 1, 0, 2, 3, and 3, 8. And then you think, okay, what if I did put 0 in here? Well, then it would be 0, -1. But wait a second. I can't include that point, so I'm going to have to make a little hole there. You can, but with this one, there's not going to be any hole because that hole is already filled in by the blue portion of the graph. So that means this one doesn't have any discontinuities. So for our domain, for f, it would be -infinity to infinity. Doesn't have any discontinuity, so we better write down no discontinuity. None. And then our domain, oh, I'm sorry, our range. Here I am saying domain again. Well, the hole's filled in. We're using all the y's. Our arrows show we're going up and down forever. And there it is, from -infinity to infinity. So this graph is continuous. Oh, boy. That's better. This graph is continuous. We had a hole, but it was filled in by the other portion of the graph. And yeah, that's a good place to stop for day 2. So with a little bit of piecewise in there, hopefully you're realizing, yes, they look kind of terrifying, but they're actually not that bad. You just have to figure out which piece of the graph goes where, and you'll be totally fine. So, talked about domain, talked about range, talked about continuity, definitely making some headway on our objectives. And here is day 2.